Hello, everyone. Good afternoon to all of you, and welcome back to our weekly lecture. So we are moving into the last unit of this, the last part of this unit, which is on real systems. Okay, so we'll be spending about 3-4 weeks, the next three weeks or so, on this topic, and each week we'll discuss something different on real system. All right. So I hope, yeah, you're all doing good after the Raya break. All right, so today we'll just look at a real system in general, and we will discuss a little bit the different types of real system available. So today's topic is mainly to introduce to you what are the different elements of real system, what are the different types of real system that we have. Okay. So at the end of this lesson, what I hope is that you would be introduced to real design, which consists of factors for using railway, and then we'll move a little bit into rail history, although I won't dwell too much into this, but I think this is more of a reading pleasure for all of you. And we'll look at the different types of rail transport and also rail transport in Malaysia, just a little bit, okay? All right, so first off, just a very quick introduction on railway or railroad. What is the definition for either one of these terms? Okay, so a railroad or railway can be defined as a narrow track of rails or plinths of irons and wood and other material made with very smooth or level surfaces. Yeah? So it has to be very smooth and it has to have level surfaces. Okay, and laid down with great solidity and truth to the required plans, so that the wheels of the carriages may meet with the least resistance. All right, so we need the rail and the carriages above it to meet with least resistance. Okay, that is practicable in rolling over them and thus reduce as much power as possible. Reduce as much as possible the power required to move a given load or to move the greatest load by a given power. Okay, so what we are looking at is very smooth or level surfaces. We want the contact between the carriages, the wheel of the carriages with the rail itself, the contact with it to have the least resistance. All right, so that we don't need so much power to move the rail forward, or we can try to reduce that the usage of power. Okay, and these are quite this particular topic, least resistance. The wheel-rail interaction has been studied over and over again, because what we want essentially is to have very least resistance so that we can propel the rail forward faster, or we can carry more load. Okay, so then for rail system, a means of transport for passengers and freight. So rail system, we use it to carry passengers and carry freight as well, whereby vehicles are coupled together as trains and pulled or propelled by a mechanized motive power. Okay, so it's coupled together. You have few different units, all linked together, or what we term as coupled together. Um, uh, Through some coupled system, and it is propelled or moved forward by a mechanized motive power. Okay, so these are all along a rail track, and usually you would have many control system to move it forward. Okay, so later on we'll see the different types of rail that we have, and for each type they have different system, different usage, different usage. Yeah? All right, so if we look at this, then we look at why do we need to study this unit, or why is this unit, or why is this part rail system embedded into this transport unit? Okay, now if we look at this table, we are comparing between railroad and trucking system, or trucks, heavy vehicles. And if we look at the fuel consumption, railroad, yes, it consumes more fuel ton miles per gallon compared to truck. That's about 4.5 times more. In terms of infrastructure, yes, it it requires higher what's that? It requires higher budget to build, or to maintain, to build, not to maintain, to build. Okay, but if we put it in terms of cost to the mileage travel, we could see that this is about 2.7 cents per ton mile, whereas for trucks, it is about 5 cents per ton mile. So it cost efficiency wise, railroad is better compared to trucking system. And for safety, in terms of safety, we could also see that for railroad, you have lesser fatalities per billion ton miles. Okay, 0.61 fatalities and about 12.4 incidents, way lower than tracking system with 1.45 to 36.4 incidents and 1.45 fatalities. So safety-wise, cost-wise, railroad has more benefit over trucking system, but we cannot also totally forego trucking system, because we still need to deliver goods right to the front of the shop houses or loading areas. You cannot use rail to transport the material up to a shop's backyard, or a shop or commercial center. So you still need truck or heavy vehicles to do that. But if we are talking about moving a lot of materials in bulk, then railroad becomes a better option. And if we look at this, yeah, so this is where we are looking at transportation. If we are comparing against distance as well as transport cost per unit, road represented by heavy vehicles, these are good for short distance or lower materials, okay, smaller materials. Then we have rail system. These are better for longer distances. But if you have very, very long distance, shipping may be a better option, depending on what you are sending. Yeah. Of course, you can't be sending something that is going to expire via ship, via maritime or shipping, if it is going to, especially food, if it is going to get rotten very quickly. All right, so if we look at the benefits of a rail system, we could move raw materials in bulk. Okay? The keyword here is in bulk. Reduce the cost of maintenance, because once you build the rail system, maintenance wise is lower. Yeah. And it also creates job opportunities, reduce pollution. And nowadays we are gearing very much into sustainable environment where we want to reduce pollution. Rail system is one good way forward. And in fact, as a matter of fact, this afternoon I was just listening into the transport policy for Australia, where they are headed to in the next 10, 20 years time. One of the guiding principle for them is to reduce pollution, and rail system is very, very important in doing that. Yeah. And rail system also promotes fuel efficiency, traffic congestion elimination, um, simply because, not because that they have their own track, that's one of the reason, but traffic congestion elimination is also because that they can move a lot of people or a lot of passengers at once. So that reduces the need to drive, and therefore it reduces traffic congestion. Yeah. Speed of transport, it could be quite speedy because it has its own track. Okay. Safety, we've seen that just now. Okay, curbing global warming, and then minimum land requirement for right of way. Yeah. Yeah. Okay, and then dependability of service under all weather conditions. All right. So those are among the benefits that we could think of, right? So now then moving into the types of rail that we have. We have now this is based on Australian system, okay, Australian rail system, but in general we still have this. We have light rail and we have heavy rail. Okay, and the term light rail here are typically meant for trams, which are found in Melbourne, a lot in Melbourne, and it operates within the road reserve environment, which shares the space with motor vehicles and cyclists. Okay, so light rail, even though they have their own track, but there's no fencing, and the light rail trams will travel on the road, similar with car. Okay, and for heavy rail, trains which transport commuters and or freight, and operates within their own reserve, where access by other vehicles and pedestrians is restricted. Right, so this one is fenced up. Usually it carries specific purpose. If it is for passengers or commuters, then it only carries for passengers. And if it carries goods, then it only carries for goods. Yeah. Light rail typically carries passengers only. All right, some note at the bottom. Modern equipment standards have tended to blur the boundaries between heavy and light rail system. For example, if light rail services share the track with heavy rail type services, then the light rail vehicle may require a higher standard of crashworthiness in the event of a collision. Okay, so this is what we see for light rail. This is tram system in Melbourne, and you can see that it shares the space with motor vehicles. Yeah? So at any time, accident could occur involving motor vehicles and trams. And Hong Kong also shares the same system. They have tram system as well, and it also shares the space with motor vehicle. I was I don't know, do you call that fortunate or unfortunate? But I was in one of it. I witnessed it myself. I was on board of a tram in Hong Kong once, and it got involved with an accident with a taxi. So yes, accident do happen between tram and motor vehicles. Okay, and for heavy rails, yep, I think we would be quite familiar with this kind of images. We would see trains, and it has its own track, and perhaps you could see different tracks siding into the main track or getting off from the main track. Okay, so for this type, it doesn't share space, and usually it's fenced up so that vehicle cannot get in, as well as pedestrians cannot enter into this part. It is very dangerous, right? Okay, then yeah. So in order for us, in order for these trains to move forward, we need some kind of power. All right, so we will have to look at what are the motive power that propels the train forward, that propels the whether it's light rail or heavy rail forward. All right, now I just go back a couple of slides, one or two slides. Yeah, yeah, this one. Now, if you look at this photo, you see that for this tram, it's attached to wires at the top. Yeah, so this wires actually supplies electricity to move the train forward. All right, and likewise for this, you would see that some of these you have some you can't quite see it here, but there are electric supplies to this at the site. That's also another way of supplying power to the train. Okay, so anyway, coming to this motive power, let's look at the different types of motive power that we have. Okay, now the mechanized or motive power for pulling or propelling a train is located either at the head or tail end of the train, or alternatively, it is distributed throughout the train. Okay, and we are talking about mechanized motive power. We are talking about locomotives. All right, so we have electric and diesel electric locomotives. It is usually attached at either the head end or at the tail end. Usually refers to separate locomotives being attached to the front, middle, or rear of the train. So if you look at this train, these three yellow colored one, these are the locomotives. Okay, so these are the ones that provide power to move the train forward, to pull the train forward. The rest are just carriages. It won't move on its own. But this tree, excuse me, this tree will then move forward on its own. Okay, because these are the ones that have power to do so. And likewise, same goes with this one and this one. These two are the locomotives that pulls the train forward. Okay, or if they are located at the tail end, then it pushes the whole train forward. Right, so a train may have just single unit of this, or sometimes you may have two or three of the same unit, depending on how many, what's the power required to move the train across that kind of terrain, and the amount of materials that they are bringing, the amount of item that they are bringing. Okay. Right, so locomotives are generally electric or diesel electric. So electric, it would be supplied from overhead here, the overhead hang equipment, okay, overhead line equipment. Yeah, so electric locomotives draw power from overhead line equipment, OLE in short, generally being 25 kilovolt AC, although there are still railways that utilize DC power. Okay, and diesel electric locomotives use a diesel engine to drive an alternator to generate electricity on board the locomotive. All right, so it's still electric based, but you need diesel power to drive that alternator to generate electricity. All right, so both electric and diesel electric locomotives use electricity to power traction motors that turn the wheels. And diesel electric locomotives carry their own fuel source that is usually located in the fuel tanks below the floor of the locomotive. Right, so the technology for diesel electric locomotive is quite advanced, particularly with the newer locomotive and their fuel consumption. Okay, and in Russia, compressed natural gas is also being used for locomotive power after a number of years of R&D. So we see that. All right, so main point here is that we have electric locomotives and diesel electric locomotives, and these two will have electric provided to the train to power the train through overhead line equipment. Right, and these are your overhead line equipment. Okay. Then we have a second type of motive power, which is electric or diesel multiple unit passenger trains. Yeah. What is the difference between this and the other one? Let's see. Now, a number of carriages, about 2 to 10 or greater, semi-permanently coupled together into one unit. Okay, and each unit has a driver's cab at either end, although some are completely automated and have no cabs. Okay, a series of units coupled together becomes a multiple unit, and the units are self-propelled. That is, there is no separate locomotive. All right. So what is the difference is that for this type of electric or diesel multiple unit, DMU in short, EMU or DMU in short, it comes together with the carriages. Okay, the units are self-propelled, meaning to say if this is one unit, it can self-propel. It can the engine or the locomotive is the engine is inside it. Yeah? So you have the engine and you also have the compartment for passengers to sit inside. Unlike the other one earlier, unlike this type, these locomotives are the engine. So there's no passenger, there's no materials, there's no goods inside these locomotives. Okay, so this will then move whatever it's carrying, and the carriages behind or in front of it will have the space for passengers and it will have the space for goods, but it doesn't have any engine. Yeah? So the engine comes from these locomotives. But unlike this type, the EMU or DMU type, each unit has its own engine, right? And usually these are used for passenger trains, and you could split it. But these are semi-permanently coupled, meaning to say it's usually quite when the few units are combined together or coupled together, usually you don't break it off any further unless there is a change in the schedule for the passengers. Okay. So an EMU takes DC or AC power from OLE, the overhead line, via a series of pantographs, or alternatively from a third rail located just above the track via a series of collector shoes. So here we see how OLE, I've introduced that to you earlier, or maybe I have some, no. OLE, I have introduced that to you earlier. Okay, so it's the overhead line hanging, it's this line hanging above it. Okay, so that's the overhead line equipment. And it may also draw power from a third rail. So this is the third rail on the track. Yeah. So the wheel of the wheel of the train will be here, and it will draw power from a third rail. Okay, so these are your normal tracks. This one. Okay, so yep, this one another photo, third rail, which is the power supply. Okay, now all right, then moving on, we also see something like this. These are what we call as bogies. Not all bogies on train are powered, and in Melbourne, each unit has 3 cars arranged as motor, trailer, motor. So you see what is this? Is that these are the wheel of the carriages. Okay, so then whatever you want above, it could be customized. If you need a passenger car, then you have a passenger carriages fixed above it. All right, and if you need to transport goods, then you would have the goods carriages fixed above it. So then this is one bogie. All right, and usually for each carriage, they have about three of these range. So it's a motor one, and then trailer, and then motor. Okay, and the units are excuse me. The units are coupled together, and you can see the couplers in this link. All right, so if we look at the advantages of having EMUs, these are the electric multiple units. Okay, when passenger demands change, units can then be added or dropped from a train. This don't usually happen unless you have passenger demand change, and therefore the rail company may want to change the transit schedule or rearrange the schedule, and then they may rearrange the resources that they have, which is the train itself. Okay, and it can offer more passenger space per track length since they operate without any locomotive. Yeah? So you don't actually need locomotive. The locomotive doesn't take up space. It will distribute traction and braking power throughout the train, achieving higher power to weight ratios and greater acceleration and braking rates. And because each unit has its own power to move, and therefore the whole train um, the whole train has power to move. It doesn't just depend on at the front or at the end of the train for the locomotive, because each unit has its own power to propel the train forward. So therefore, each unit also has its own traction and braking power. All right, and this is a very higher power to weight ratio. This is something that we, excuse me. Now, higher power to weight ratio is something that we want for train system, for rail system, something that a rail system really requires. With higher power to weight ratio, what it means is that for a train to move forward, it really requires a lot of power. Imagine you have such a long train and the train is stationary. It's at a stop and you want the whole train to start moving. You really need a lot of power to push that train or to pull that train forward or to whichever direction. Okay, and the train itself, if it is empty, it's already heavy. What more to say if you add in load such as either passenger or goods, yeah, or materials or goods, then it becomes even more heavy. All right. So if you have very little power and you have a lot of very high weight because of the train weight and because of the goods, then the train finds it very difficult to move forward. Okay. So really what we want is to have a very high power to move all those weight. Okay, so higher power to weight ratio is something that we want. So with an EMU, every single unit um, has its own power to move forward. Then it actually achieves a higher power to weight ratio, rather than the earlier one. We use locomotive, so it's either at the end or at the head end of the train. Then it has to push the entire train forward. Yeah, so that's a bit more difficult. Okay, so with higher power to weight ratio, that will also achieve greater acceleration and has a better braking rates. All right, and they are popular on commuter and suburban rail networks around the world due to their fast acceleration and pollution-free operation. All right, so yeah, this is a bit of history. First EMU started operation in 1893. That's well over 100 years ago. Okay, and it uses the Liverpool Overhead Railway using third rail electric pickup at the track level. Yeah. Okay, now then a DMU is very similar to EMU, except that it has diesel engines for the train are located below the floor of the train. Diesel is the fuel tank, as is their diesel fuel tanks. All right, and same configuration. Every unit has their own power system. All right then. Yeah. So enough about power system of the rail. We'll just move very quickly through the history of rail. I don't want to go through very deeply into this, but I think you can all read from the slides on the history. But if we look at this, just want to draw some attention to some of the things that carried forward to these days that made it the rail that we have today. Okay, so the first commercial privately funded railway successfully carried passengers. Initially, rail system was used for very much for mining, and it wasn't powered by what's that? By all this diesel or steam engine. It used to be steam engine and so on. All this came a bit later. Now, the very early days, um, we use horsepower, literally horse. We use horses to draw the rail, the carriages on rails such as this, but it was not iron rail. This is iron rail. The olden days one, it was wooden rail. And it's not as flat and smooth as what we experience nowadays. Okay, so three elements. The engineers from this, what's that? Liverpool and Manchester Railway. They identified three key elements to distinguish railways from other forms of transport. Okay, so the three elements that we still use until today: the edge rail, okay, which is this, the flange wheel. Sorry, this is the flange wheel. Okay, and then the edge rail and the mechanized motive power. Right, so the power that it uses. All right, so these three things are still these three elements are still in use until today. All right, so I think the timeline, you can read it on your own. I don't want to go into this. Okay. Yep, today there are around 1.37 million route kilometer of railway worldwide. And we have come very far from the first railway train, because these days train can carry passengers at maximum speeds up to 10 times as fast as what they would have traveled in 1830. If we look at the speed, 1830, about 50 kilometers per hour. If you drive, probably it's faster than this. But fast forward 2006, we have about 574 kilometer per hour. So that's as fast as an airplane. And carry freight up to 10 times the mass on each wheel set of a wagon that could be carried in 1830. So if we look at the comparison, 1830 versus 2012, 4-ton versus 42-ton. Yeah, so that's how advanced we have become. What does this mean? It means that nowadays we can travel faster, arrive at our destination in a shorter time, and we could move a lot more materials in just one trip. Yeah? So production is higher, and we could really get goods to destinations in a shorter time. Okay. If you have some free time, you could look at this. This is the 1804 locomotive that is recreated. Steam locomotive as well. It's a replica. And this is a modern one, TGV at 574.8 kilometer per hour. Okay, and these are also for your reading pleasure. I put it on the slides as well. For your reading pleasure, rail development in Australia. And you could see that the first rail in Australia was in Newcastle in 1821. And then slowly from there it developed. But one thing that you need to know is that because for Australian side, when they developed the rail was developed at different locations. So each state, they have their own rail system. And therefore, you could see that later on, you would see that there are different sizes of rail uh, gauges that were used across Australia. Yeah. They have, since then, they have tried to standardize it. Yeah. So this is railway map of Victoria for Melbourne in the Victorian state. So again, yep, I think I'll just pass this off for you to read on. Okay. Are we good until this point? All right, so moving forward, we look at the types of rail gauges that we have, okay? And like what I've said just now, because in Australia, the rail system started at different places, and each state, they have their own rail system. So then you could see that these are the three different rail gauges: broad gauge, cape gauge, and standard gauge. So the sizes here: 1600 mm, 1067 mm, and 1435 mm. So 1006 broad gauge, Victorian suburban and regional services, Adelaide suburban services, only applies to these areas. Okay, and then cape gauge, this applies in Queensland, Tasmania, and West Australia. And standard gauge applies to all Australian mainland states. So you could see different sizes. Now, what I mean by all these gauge sizes, just give me a second. Okay, so what I meant by all this. So this, okay, the gauge size, we are referring to this between the two rails on a track. Okay, so this is one track. So on one track, there are two rails, and the size, the width of this, the width between the two rails. Okay, so that's the gauge size. So that gauge size, so we have different gauge sizes: 1006, 1067, and 1435 mm. Right. So in 1962, a new standard gauge line was opened between Melbourne and Albury, enabling passengers and freight to be transported between Melbourne and Sydney without break of gauge. Whenever we have a break of gauge, that means if, let's say, you want to go from Queensland to Sydney, for example, you have different gauge sizes. And what happens is that the train cannot move over to the other gauge. So imagine if, let's say, you have one line using 1006 mm gauge size and another line using 1067 mm. So this first train will not be able to go over to the second set of track because the gauge size are different. So then passengers, they would have to stop at this middle station and change over to the next what's that, rail system, to the next train, so that they can move on using a different train with a different gauge size. Yeah, so then standardization soon followed between Melbourne and Albury, between Melbourne and Sydney, without break of gauge. So that means transshipment of freight and passengers. It's once off from start to end. Okay, then further gauge standardization was undertaken in subsequent years. And 1995, trains could travel continuously between Brisbane and Perth via Sydney, Melbourne, and Adelaide on a standard gauge track. So we see that more and more standardization has taken place all over Australia. And in 1998, the Australian government-owned Australian Rail Track Corporation took over the management and control some 8,500 kilometers of standard gauge track, okay, primarily through direct ownership and long-term leases. Okay, so in 2004, standard gauge line was extended from Alice Springs to Darwin. This is towards the north of Australia. Yeah, so they Melbourne and Sydney. Sydney is on the west side of, sorry, on the east side of Australia. Perth is on the west side of Australia, and Alice Springs and Darwin is towards the north. Okay, so once they have all that standardization done, then you could travel very smoothly between cities. All right, so then we move on to look at passenger and freight rail system types, the different types of rail system used to carry passenger and freight, okay, and goods. Yeah. So 7 passenger and freight rail system types are considered here. Each system type has its own particular operating characteristics, and the infrastructure must be designed to cater for that system. All right, so here we see safe working and operational systems are similar for all system types except like rail. Yeah. So we see for passenger rail, we have all different types catered for different use. We have metro, tube, subway, underground. These are mostly short travel. Then we have suburban, regional, whether it's metropolitan to non-metropolitan. Then we have intercity travel or intermetropolis travel. And then we have long distance travel, and we also have light rail system. Okay, so all these are catered for passenger needs, passenger movement. And for freight movement or movement of goods, we have intermodal freight and heavy haul freight. Yeah, we'll see what are these. So first off, excuse me. So first off, we have underground or tube or metro or subway. Different places they use different names to what do you go so to describe this rapid transit or mass transit. Okay, I think some places they use tube, some places they use metro. All right. Large number of stations for distribution of passengers in CBD. So this is, like I said just now, this is used for very short distance, and usually it is in a very busy central business district area, okay, in downtown areas. We do expect a lot of passengers, very densely populated areas. Then it is good to use underground or tube rapid transit. Okay, and we have usually what the characteristics is that we have a lot of stations, and the stations are spaced very closely together. Maybe a few 100 meters away, you would have one station. Yeah. So the idea is so that people can really access to the different locations in the town or in the city. All right, and services city services city terminal railway stations, suburban, regional, interpolis. All right. Yeah. What it means is that it helps as it serves the city railway terminal stations. And so if you want to travel longer distance, you would have to change over at change over railway station, and these tubes usually would fit into this station. Okay, and services run from terminal points on one side of the city to a terminal point on the opposite side. Okay, and some may have circular services. Usually you have one start point and it travels all the way to an ending point. This is a very typical route, and then you have another one maybe from east to west, one from north to south, something like that. Okay, or some services, they have a circular type. It just go starting point and it goes one round and come back to the same point again. And for CBD sections are usually in tunnel or elevated on viaducts above street level. Okay, and you see here the different names given: underground or tube in London, metro in Paris, subway in New York. And the lines providing the services to a city may be on separate systems so that interchange between them is undertaken at multi-level stations, usually underground. Okay, what we see is that because you have now for this type of transit, you have to have their own their own rail movement. They cannot share the tube for different direction. Yeah? So usually what we have is you have, let's say, two lines, one to go this direction and one to come back. And then you have another one above it. Yeah? So at this change location, um, this usually is a station. And for this station, you may have multiple layers underground. Yeah? So you have to take lift or elevator to go to the first level if you want to travel in this direction, and you have to go further underground if you want to travel in the other direction. Okay. Yeah, in Hong Kong, it's known as MTR, Mass Transit Rapid. So I think so, Mass Transit Rapid, something like that. They have lines with lines on 3 different levels. Some lines may share track with each other for a portion of their route or operate solely on their own right of way. And imagine for this, we are in transport class, so we are only concerned about the route, okay? But if you are in geotech class, then you would be concerned of the underground construction, tunneling. So you'll be tunneling one tunnel, another tunnel in different direction. So if you have 3 level, you would have 3 different underground tunneling. So it's a very geotech heavy type of construction. Train length for both types may vary. In peak hours, urban trains are usually about 6 to 8 cars in length. This is the characteristics, okay, 6 to 8 cars in length. And it's very good for moving high passenger volumes for short distances around urban areas. So, and typically we don't provide a lot of passenger who are seated, about 100 passengers seated, or crush loads of around 160. Crush load means packed like sardine. Okay, so typically we see this during peak hours. People would just push their way in, so that is crush load, right? And yeah, trains usually have fewer seats, more standing rooms, and among the characteristics also is that the doors on each side of the carriageway may vary from 3 to 4 doors. You have to have this kind of, for the stations, you have to have this kind of platform edge doors. operate similar to a lift, open and close after arrival and before departure, improve safety, ensure passenger confidence, reduce the cost of station air conditioning, and prevent litter and other matter being deposited on the track. Okay. Right. So urban railways may also have automatic train operation. Okay, some have drivers, some don't. And trains, yeah, some may be driverless. Okay. Yep. Another one, London Underground rolling stock. This one opened in 1863. Completed 150 years of operation on 9 January 2013. Okay. Yeah. So if you missed out on the third rail just now, this is the one. All right. Then next up, we have the suburban or regional travel. This means that it's between metropolitan to non-metropolitan. Okay, it's regional travel or travel to same city, but it could be to suburban areas. So this distance usually would be slightly longer, and therefore we see that what we want, suburban usually are places where people stay. And you have houses there, and therefore uh, these are the people who then commute to CBD areas. Okay, so journey time and attractiveness due to guaranteed frequency. A very high frequency service provides capacity, and it uses EMUs with very high acceleration and braking and minimum dwell time at stations. Dwell time here refers to the time it stops at a station. Okay. You also don't want the train to stop too long at the station because then it will be a waste of time. Yeah. Signaling control system, it requires some form of signaling. It usually has automated ticketing, okay, and personal security through open design, alarms, etc. Okay. Design for lowest maintenance train and infrastructure and maximum segregation of services, but easy interchange. Okay, so this is for reading. This is specific suburban regional travel, specifically for Australia. So the characteristics here is that for suburban and regional travel, they have more seats offering because of the longer travel distance, travel time. Okay, and we also may have a bi-level passenger carriages, two level, okay, double decker to increase passenger capacity. So Sydney, for example, here, Sydney utilizes EDCAR double-deck trains for its whole fleet. And suburban commuter rail system may operate at lower frequency or headways than urban rapid transit, because the volume that it carries are not that high, so it may have lower frequency. A distinguishing feature between metropolitan and non-metropolitan trains may relate to the number of doors on each carriage and whether they are fitted with toilets or not. Okay. Now, usually what we see is that for metropolitan, these are big cities. Non-metropolitan, these are smaller cities or even towns, usually further apart. And metropolitan, usually it's closer, closely spaced, yeah? Closer together. All right. So if it is closely spaced, we are talking about more number of doors. And if it's further distance away, then we look at lesser number of doors. Uh, those are usually quite important because then it allows your passengers to board and alight easier. If you have a lot of doors, passenger could go in and out very easily. Something like your metro underground, those are wide doors and you have a lot of doors. Okay, then passenger goes in and out very easily, very quickly, because we want minimum dwell time at the stations. Okay, so why are Australians' urban railways different to Europe? Now, in Europe, in European cities, heavy passenger rail networks were developed primarily for intercity travel, not so much for city travel. For example, Paris to London. Okay, but for Australia, it is more about connecting the local port to surrounding areas or surrounding hinterland, right? And then subsequently, it expanded to the suburbs. All right, so this is where the people who are staying at the suburbs would then come in. Okay, so geographically they are different, and the purpose that it was initially built for are also different. And train formations or consisting of EMUs and DMUs, we see this for Australia. And as stated, EMUs operate in all capital cities of Australia with the exception of Hobart. And in Sydney, EMUs provide the bulk of non-metropolitan services. Yep. So this is metro. This I think is Sydney. Okay, so we could see that. Yeah, so this is the overhead line equipment that was used to supply the electricity to, this is the train. Okay, this is the EMU unit here. So then this overhead line equipment supplies the electricity to power the train. And this type of trains are typically used for non-metropolitan services. So then next we look at intercity trains travel. Right. So before this, we look at the first one just now. We look at just urban area, very densely populated, and then we take one step further. We we look at people who are staying at the suburbs, traveling into the city. So frequency is lower, the distance is slightly longer, and if we are talking about intercity, the distance are even longer, up to 400-kilometer journey. Yeah, so it's between two cities. And average speed of the trains will fetch up to about 160 to 200 kilometer per hour. Maximum can go up to 320 depending on the type of train, depending on the train engine. All right. Station spacing from one station to another is about 50 to 80 kilometer. Okay. And high train type, very high capacity with fewer onboard services. All right, so other features, we'll look through these other features. Attractive overall journey time through, high frequency or regular stopping patterns at all the different stations along the way, okay? And high acceleration or braking, low station dwell time. Again, it will stop at the station for a short time only. Efficient guaranteed connections between intercity services at hubs with other transport modes at station. This is also important with other transport modes at the station, because when you have train, you cannot be stand alone. In the first few weeks of this unit, we learn about intermodal. You have different mode of transportation. Yeah, so it is important that a station has different modes of transportation system. Okay. Yeah, designed for reliability, low weight energy use, and traction power. It has a bit of traction power issues because of the train it uses and because of the locomotive system. Personal security, because of the open train design. Okay, and conventional intercity trains usually consist of a head-end locomotive. Yeah, so this type of train will use a head-end locomotive. Intercity services may share tracks with freight services and can be hauled by the same locomotive types. Now, another type of intercity train, we may use high-speed rail, HSR, which may operate at a speed of 320 or beyond. Okay, and these are really, really high speed with very smooth rail. Some of the rail, some of this intercity train, it may produce some clickety sound because of the track it uses. But for HSR, it's very smooth. If you sit inside, there's no sound, and you just don't realize that you are traveling at that speed. And if you are using HSR, they generally operate in 8-car sets. And some HSR trains have integrated locomotive. Okay, others have motors distributed throughout the train with passengers sitting in what would be otherwise be the locomotive section. Okay. Yeah, so HSR trains operate on the dedicated right-of-way. So train frequencies are usually fairly high, about 5 minutes once. Yeah. So the control system must be really good, because then you have to ensure that about 5 minutes you have HSR arriving at the station. But HSR could also operate on a conventional track so that it can gain access to locations where a dedicated track cannot be built. Okay. And if we look at the maximum train speeds for HSR, currently is about 300 to 320, but there have been trains that are tested at higher speed. TGV tested at 75 kilometer per hour. Okay, and for HSR train length, these are really long, but not as long as the ones that we are going to see after this. Okay, yeah, so the London, Paris, Brussels train has a length of 393, about 400 meter in length. And imagine having this about 400 meter every 5 minutes. So the whole system has to operate, the whole rail system has to operate in a very controlled environment. So just an example, this is Japanese Shinkansen HSR. Very, very smooth track. You really have to have very, very smooth and level track so that passengers inside will be very comfortable. Okay, so next up we look at intermetropolis. Journey length is more than 400 to about 1,000 kilometer. Speed is about 320 kilometer per hour max. Station distance usually very far apart, because this we are talking about intermetropolis, inter large cities. The infrastructure for this type of train system segregated for main high-speed journey section, but operates in conjunction with other trains closer to the city center. All right. In Southeast Asia, there are extensive plans for HSR connecting each country, and we already see both South Korea and Taiwan operate their own HSR services. Not cheap, but it's fast, really fast. And for long distance trains, particularly in these countries, Australia, Canada, China, Russia, USA, what they have in common are the geography of their country are really, really big, really huge. So if you want to travel from one location on the east to the west, it will take you really long, days even. So for that long distance train, they would have to provide sleeper and seating accommodation for the passengers. But this type of trains are also very poor with the time, um, sometimes classified as tourist trains. And if we look at this, Russian Railways runs the Trans-Siberian Express from Moscow to Vladivostok via southern Siberia, and total distance is 9259 kilometer, about 8 days, passing through 7 time zones. So these are really long distance travel. Okay, for Australia's longest journey on the Indian Pacific, from East Coast to West Coast, Sydney to Perth, 4352 kilometer. So the length of the trains up to 22 carriages in length. Okay, and for the last passenger rail system, we have light rail transit, LRT, or also known as streetcar, sometimes tramway. Okay, what differentiates this type of system is that it has lighter axle loads than the trains that we have seen so far. Okay, and it could be either a single vehicle or articulated, but if design permits, may be coupled together. Okay, and lower average speed and very closely spaced stops. You see, a few hundred meters, you have one stop or one station. Metro, about 1 to 1.6 kilometer. Okay, so because the axle loads are lighter, because the axle loads are lighter, the construction for these are also easier and the costs are lesser. Okay, just give me a second. I think my battery is about to go off. Just let me switch on. Okay, so yeah, so then generally two types of LRT. One is tram, run along the street, and the other type of light rail is still LRT, but it has its own right of way, separated from road traffic. Okay. So this one, the construction cost usually a bit higher because then you have to acquire a different, construct a different set for rail for the rail system. Okay, I'll skip this. I think, yeah. All right. So then, yeah. So for LRT, usually the development is towards a transit-oriented development to minimize car use and maximize public transport use. Now, if you recall from our first few first few topics of this unit, I have said that demand supply is that we try to shift passengers or car drivers into not driving and into using public transport system. Okay, so in the very first place, we as government, they also have to provide the system for the public to use. And then we can look at transit-oriented development, okay, to try to minimize the car use and to maximize public transport use. And could be extended further by the adoption of shareable private transport, sharing economy. And what is the consequence is that we would have car sharing, ride sharing, or even bike sharing. Okay, so all this relate it back to what we have learned from the first few topics with the aim of reducing road congestion and air pollution and personal vehicle ownership and associated costs and parking demand. right? And then lane dedicated to parking spaces. We don't need that many because if you don't drive, you don't need parking spaces. Then we can dedicate this lane to other better use. And enhancing mobility for those who do not own a car. Yeah, from the earlier talk that I attended just now on the Australian transport future, they said in a survey about 30% of people do not have ready access to a vehicle. So then all these people would need to be provided with public transport. So here we have Hong Kong's tram, Melbourne tram. Okay, so all these are common, sharing the road space with vehicles. Okay, then we move into freight services just a little bit, very quickly. Right, rail carries approximately 10% of all the freight or goods hauled in Australia, and this typically has lower speeds compared to passenger trains. Okay, and for freight services, they have to have very specialized wagons because it depends on the type of goods that are being hauled. Okay, so if you are carrying, say, beans, grains, then the wagons would have to be customized to carry beans and grains. Comparatively, if you are carrying, say, for example, if you're carrying sand or cement or even what's that, concrete panels, then it will have different type of wagons. Okay. So freight trains are very efficient with economy of scale and high energy efficiency. Very good for bulk movement of materials. And metal wheels on metal rails have significant advantage of overcoming the resistance compared to rubber-tired wheels on any road surfaces. Because usually these goods, if you move it in bulk, these goods are very, very heavy. So having metal wheels, this would have more resistance and it would last longer. Okay, so yep, I've put here bulk handling represents a key advantage for rail transport. Okay. So if you look at this, typical bulk cargo includes coal, iron ore, grains, liquid. So some are in powdered form, some are in grain form, some are in liquid form. So you have different types of materials, cargo, that you have to really customize the wagons. Okay, so heavy haul freight system, the long train length up to 300 wagons, 300 wagons. If you compute this out, it could reach a few kilometer train length. Heavy axle up to 42 ton. And this information would be required if you are to calculate how many, in terms of the operation, how many wagons do you need, how many locomotives do you need to provide later on. We'll look at that later in the tutorial. Okay, so unit trains, these trains use specialized rolling stock and other mechanisms for moving a bulk material or commodity from a single origin to a single destination. Say, for example, from a mine to a power plant or steel mill. Right? And these trains are highly efficient since no intermediate handling occurs. However, often the freight wagons return empty because it's one way, one direction. Let's say from a mine, you load it and then it moves to a processing, either a power plant or to a steel mill. Then you unload it at this location. Okay, so then it goes back to the mine again. Then it's empty. But it's efficient because it's it's really meant for that purpose. Yeah. Okay, so then there are two alternative types of wagon. The wagon, depending on what is the material being carried, you could have a bottom dump hopper wagon, operate with air-operated doors for material discharge beneath the floor of the wagon. Wagon must have sloping sides at angle, okay, at angle of repose for materials to flow. All right, so this is good. Bottom dump hopper wagon. This is good for materials that are generally grainy, like sand, for example, or aggregates. And then you have rotary dump or tippler wagons. This would dump hanging upside down inside the wagon. These are used for sticky materials. Okay, maybe we try and watch this. Let me just open that. Okay, so this one is a bottom dump. You see that the bottom door open. And you see these are the materials. Open further. The material drop.
Right, then you come in uploading.
Okay, and for this type, the second one, which you can see, this is rotary dump. Okay, so I hope that gives you a little bit of idea into what is a bottom dump and a rotary dump tippler wagons. Yeah, some further videos that you could watch. Yeah, you could go to this. Okay, now container or intermodal freight rail system. We have transport intermodal containers or flat or well wagons. Okay, so and for this container, it will carry a lot of different containers for companies, and the length, the container length vary from about 6.1 meter to 16 meter. Okay, and containers may be stacked on a train, or some single, some are double stack mode. And we see this very often at port areas. Okay, so some issues is that with this is that you need to have sufficient clearance. The facilities provided need to have sufficient clearance for a double decker, double stack containers to pass through. All right, and yeah, so here I said that container or intermodal freight system, you need to have, usually this is at port locations, and we would need to have container gantry cranes to transfer between train and ship, to load it between from train to ship or ship to train. Okay, other types of intermodal freight system, we have containers are tank containers for carrying liquids or chemicals, hazardous or non-hazardous chemicals. Okay, so we may have that type. All right. Yeah, the rest not so important. Okay, so yeah, you can again, you can have a look at this. What's that videos? I think one of it, you would see a very long one, a very long heavy goods vehicle. Let me try this one. So you see different items being carried because of the wagons. These are empty ones. Okay. Right. Yeah, so at port sections, when you have container trains, then you need to have gantries such as this to actually transport or transfer these containers onto the rail. This is the rail. Okay, and to transfer it to either to the rail or from the rail to the ship. Yeah, so we really need these facilities. Here's another one, from train to the truck, okay, or from the truck to the train. All right, so these are to transport goods, and for this type of trains, they usually do not have passengers. Yeah, so today what we have seen is we have passenger trains, different types of passenger trains, and as well as we have trains that are meant for goods only. Okay, so yeah, with that, I end my lecture here. Thank you very much for tuning in today. Any question? All right, good. I don't see any question so far being posted. All right, so with that, I think I'll end it here. Thank you very much, everyone. Have a nice evening, all of you. Yep.
Total